So we continue our discussion with cross product in vector algebra. We have already discussed dot product of two vectors. If you remember, dot product of two vectors is a scalar, but cross product of two vectors will be a vector. So the cross product of two vectors, the cross product of vectors A and B, this will be defined as A cross B, and it is equal to the product of the magnitude of the vectors into the sine of the angle between the vectors. That is, you can say the cross product of vectors A and B is AB sine theta, where theta is the angle between A vector and B vector. It is the angle between A vector and B vector. So now, obviously, A cross B, AB sine theta, it represents the magnitude of the vector only. In order to indicate the direction, we write it has n hat. Now this n hat provides the direction of the vector, which is A cross B. So A cross B is AB sine theta n hat. It means that the cross product of two vectors is a vector whose magnitude is AB sine theta and its direction is provided by this unit vector. This unit vector n hat is perpendicular to the plane containing A vector and B vector. So remember that this unit vector has a direction which is perpendicular to the plane containing A vector and B vector. So suppose this is a plane which contains A vector and B vector. Suppose this is A vector and this is B vector. They are inclined at each other at some angle theta. So A cross B is a vector whose direction is perpendicular to this plane in which A vector and B vector are present. Now the perpendicular can be out of the plane, the perpendicular can be into the plane. But when we are defining the cross product of two vectors A and B, then the direction of n hat is in the direction such that if we rotate the fingers of our right hand in the sense from A to B, the direction in which the thumb points is the direction of n hat. So this direction of n hat is in this manner. Because we are defining A cross B, we will rotate the fingers of our right hand in the sense from A to B. If we rotate the fingers of our right hand to be precise, right palm, you can say. If you rotate the fingers of your right palm, then n hat is in the direction of the thumb. So if you rotate the fingers of a right hand in the sense from A to B, in the sense from A to B, from A vector to B vector, then n hat is in the direction of the thumb. So that means I am using the right hand rotation rule. So A to B, if I rotate, suppose the plane of the board contains the vector A vector and B vector, and A vector to B vector, A cross B means rotate the fingers from A to B. Then obviously the thumb is pointing out of the plane of the board. So in this sense you can say n hat is perpendicular to the plane of the board because the vectors A and B are on the plane of the board. If you find B cross A, then you have to rotate the fingers of your right hand from B to A. So if you do that, B to A, then your thumb will point into the plane of the board. So it depends on the sense of rotation from A to B or B to A. Accordingly, the unit vector might be perpendicular to the plane of the board. It might be perpendicular out of the plane of the board, or it may be perpendicular into the plane of the board. So this is also called as right hand thumb rule or right hand palm rule. Another rule can be utilized to find the direction of n hat. That rule is called as the right hand screw rule. So if you rotate a right handed screw in the sense from A to B, the direction in which the screw will advance will be the direction of n hat. So if you rotate a screw in the sense from A to B, so in this sense it is in the anti-clockwise sense. So if you rotate a right-handed screw in the anti-clockwise sense, the screw will unscrew in the outward direction. The screw will advance perpendicular to the plane of the board in the outward sense, A to B. That means you are rotating the screw in the anti-clockwise sense. Then the screw will come out of the plane of the board. So in this case, the n hat is perpendicular to the plane of the board in the outward sense. But if you determine B cross A in this manner, then B to A, you will rotate the right screw in the clockwise sense, and the screw will penetrate into the board, and then the unit vector n hat will be perpendicular to the plane of the board. So whichever rule is convenient, you can use it, right hand palm rule or right hand screw rule. Both are used to determine the direction of n hat. Remember, n hat is perpendicular to the plane containing the two vectors A vector and B vector. It is either perpendicular in or perpendicular out. And whenever it is perpendicular in, we use a symbol to do so. So suppose A cross B. Suppose this is A vector, this is B vector, and we are determining A cross B. They are inclined to each other at an angle theta. So in this sense, A cross B, n hat is perpendicular out. So this will be represented as n hat, and the symbol that we use is a dot with a circle. This represents perpendicular out. Suppose this is A vector and this is B vector. We are determining A cross B, A vector cross B vector. Then we are rotating in the sense from A to B, so it is perpendicular in. So this perpendicular in is usually expressed as cross with a circle over it. This represents perpendicular in. So cross product of two vectors is definitely a vector. The cross product of two vectors is always a vector, and that vector has a magnitude which is AB sin theta, and its direction is along the unit vector perpendicular to the plane containing A vector and B vector. So now, if you find the modulus of this vector, obviously that is AB sin theta, because modulus of n hat is 1, it is a unit vector. So modulus of this cross product is just AB sin theta. So now we can define this cross product with respect to the unit vectors along the x, y and z axis. So suppose we take the cross product of a vector with itself. A vector cross A vector will provide you a zero vector or null vector. Why? Because a vector is inclined with itself at an angle 0. The angle between the same vector taken twice is obviously 0. So you can say that precisely A vector cross A vector is modulus of A sine 0 degree n hat. So obviously that is 0. Now this is actually 0 means this is not scalar 0. This is a null vector. Here 0 indicates a null vector because cross product has a direction. So here 0 does not mean the scalar value 0. It means a null vector, a vector pointing in any arbitrary direction. So this is actually a null vector. So now, because of this n hat, A vector cross B vector and B vector cross A vector are never equal. A vector cross B vector is AB sine theta n hat. Then if you find B cross A, the magnitude remains the same, but the unit vector is opposite to the previous one. So therefore you can say that A vector cross B vector is minus of B vector cross A vector. So they are not commutative. So cross product of two vectors is not commutative, just like dot products which is commutative. So you say that they are not commutative. Not commutative. So suppose it is given that A vector is perpendicular to B vector. Then A vector cross B vector is AB sine 90 n hat, which means in this special case A cross B is AB n hat, and the magnitude, if you say, of this cross product will be just AB, because sine 90 is 1. So in this manner we can define the cross products of the unit vectors along the x, y and z axis. So from the first property, cross product of a vector with itself is 0. So from here you can easily say that if you take the cross product of the unit vectors along x, y and z axis with itself, that is obviously 0. J hat cross j hat is 0, I hat cross I hat is 0, and k hat cross k hat is 0. And from this, A cross B, if A vector is perpendicular to B vector, then you can certainly say that I cross J will give you k hat. Because you see, if you find I cross J, they are perpendicular to each other, you will get modulus of I, that is 1, modulus of J, that is 1, and sine 90 is 1, and the unit vector, that is n hat. That means the unit vector perpendicular to the xy plane is obviously the unit vector along the z axis, that is k hat. Similarly, you can say j cross k is I hat. That is the unit vector perpendicular to the yz plane is the unit vector along the x axis, that is I hat. Similarly, you can say k cross I is j hat, because the unit vector perpendicular to the zx plane or the xz plane is the unit vector along the y axis. So it will be j hat. Obviously, if you take the opposite, that means if you take j cross I, you will get minus k hat. If you take k cross j, you will get minus I hat. And if you take I cross k, you will get minus j hat. So the condition for perpendicularity of two vectors is that their dot product is 0. We have already learned it. And now the condition that two vectors are mutually parallel is that their cross products will be 0. So two vectors are mutually parallel, it means that their cross product is 0. This is a necessary and sufficient condition, you can say. two vectors, say A vector and B vector are mutually parallel, that means they are indeed parallel only if their cross product is 0. So this is a necessary and a sufficient condition to express the parallelism of two vectors. Two vectors are parallel if their cross product is 0. While studying dot products, we also realized that two vectors are necessarily perpendicular if their dot product is 0. So now we can express the cross product in terms of their components. Suppose A vector is expressed as Ax I hat plus Ay j hat plus Az k hat, and B vector is expressed as Bx I hat plus By z hat plus Bz k hat. Then what will be A cross B? So now you check it. I cross I will be 0, J cross J will be 0, K cross K will be 0. So we will never get these components Ax, Bx, Ay, By and Az, Bz. You will not get in A cross B. So you have to consider I cross J and I cross K. So you will get Ax I cross J, that is K. So Ax By k hat plus Ax Bz I cross K is minus J. So this is minus J hat plus Ay Bx J cross I is minus k hat. J cross J is 0, so there is no Ay By. Ay Bz J cross K is I hat plus Az Bx K cross I. K cross I is minus J hat. K cross I is J hat. So this is J hat. Az By K cross J. K cross J is minus I hat. So now you can write A cross B as coefficient of I hat. For I hat you have Ay Bz and Az By. Ay Bz minus Az By plus, take the coefficients of Z hat, you get Az Bx minus Ax Bz J hat plus the coefficients of K hat, that is Ax By minus Ay Bx K hat. So this will be A cross B when A and B are expressed in component form. But this might be difficult to remember, so we will apply the trick of determinants in order to remember this. So what we get is Ay Bz minus Az By, Az Bx minus Ax Bz, and Ax By minus Ay Bx K hat. So we use a trick that is called as the trick of determinants in order to remember this. So we have to write this A cross B and its components in the form of a determinant, and then we can remember it. I hope you have copied it So let me omit this and we will get the same result if we apply the determinant. So this determinant form for remembering for A cross B, we will express it in this manner: I hat, j hat, k hat. We will write the coefficients of I hat, j hat and k hat. Because A comes first, we will write for A. Then we will write for B, that is bx, by, bz. Now, from here on, for I hat, you will take positive. You will take alternately positive and negative. For I hat, you take positive I hat. You have to close the row corresponding to I hat and the column corresponding to I hat. If you close the row and column corresponding to I hat, you are left with these four values. These four values, that is ay, az, by, bz, and you have to cross multiply and subtract. So closing the row and the column of I hat, you are cross multiplying ay, bz, subtract by, az. Then first positive I hat, then alternately it will become positive and negative. So now minus j hat. You have to close the row and column corresponding to this j hat, and then you have to cross multiply. You will get ax bz and minus bx az. Then again k hat, it will be positive. If you close the row and the column corresponding to k hat, you will get ax by minus bx ay. So if you can compare with the previous result, you will see that exactly the same result is obtained, but in that case I wrote plus j hat and this was opposite. It was az bx minus ax bz, but we have taken minus, so this remains the same. So this is the easy way of remembering A cross B in determinant form. We will take several examples. So using the cross product of vectors, we can find the area of a parallelogram and we can also find the area of a triangle. So let us calculate the area of a parallelogram using cross product. Suppose we have a parallelogram ABCD whose adjacent sides are expressed as vectors. So suppose this is a parallelogram, its adjacent sides BC is represented by A vector and the side AB is represented by B vector. The angle between A vector and B vector is suppose theta. So the angle between A vector and B vector is theta. Now, in order to find the area of the parallelogram, what we do is we actually draw a perpendicular from AD on the base BC of the parallelogram. So if you can calculate sin theta from this particular triangle, suppose this is triangle ABM, sin theta will be AM by AB, or you can say AM is AB sin theta, which means AM, that is the perpendicular, is equal to AB. AB is actually the magnitude of B vector, so we will write it as B sin theta. So we have represented the perpendicular as b sin theta. Now the area of the parallelogram ABCD is equal to the base into the height, we know that. So area of parallelogram ABCD is equal to the base into the height, that is BC into AM. Obviously this is not the cross product, this is the multiplication of the two sides, the base into the height, BC into AM. What is BC? BC is the magnitude of the side A, so that is A, and AM is B sin theta. So if you remember, cross product of two vectors was AB sin theta n hat. Now we get the magnitude of this one, so this we can write as modulus of A vector cross B vector. So the conclusion is that if the adjacent sides of a parallelogram are represented by A vector and B vector, then its area is the modulus of the cross product of the vectors. This is how we can find the area of any parallelogram. If we follow this, we can also find the area of a triangle. So suppose instead of the parallelogram we have a triangle, suppose the triangle is ABC, then also we can find its area, and that will be half of A cross B. So if you have copied it, I can omit this one. So suppose we now have the triangle ABC. So this is area of triangle whose adjacent sides are represented by A vector and B vector. We know that area of the triangle is equal to half into base into height. Base is BC, height is AB. Sorry, it is AM. Now, as in the previous example, BC is the magnitude of the vector A and AM was B sin theta. So this becomes half of AB sin theta. And what is AB sin theta? It is the modulus of the cross product of A vector and B vector. So if the adjacent sides of a triangle are represented by A vector and B vector, its area is half the modulus of the cross product of the vectors. So now, if in a parallelogram, instead of the sides, the diagonals are provided, then also we can calculate the area using the cross product. Let us do that. So again we will come back to the area of the parallelogram whose diagonals are provided. Whose diagonals are provided instead of the sides. So suppose we have a parallelogram Suppose this parallelogram is named as O, A, B, C. Obviously you can see that the diagonals are AC and OB. So these are the diagonals. The diagonals are AC and OB. Now suppose OB is A vector and AC is B vector. That means the magnitude of OB is the magnitude of A vector, that is A itself, and AC is magnitude of B vector, that is B itself. So suppose the point of intersection of the diagonals is point P. We know that the diagonals bisect each other in a parallelogram. So as it bisects, as the point P bisects AC and OB, so OP vector is half of A vector and PB is also half of A vector. Direction is same and the magnitude becomes half actually, because diagonals get bisected at the point of intersection. Similarly, AC, which is another diagonal, it is bisected, and so AP can be written as half of B vector and PC can be written as half of B vector. Now remember, in order to find the area of the parallelogram, we want to find the adjacent sides, and then if the cross product of the adjacent sides can be determined, we can easily find the area of the parallelogram. So now in triangle OAP, if we use triangle law of vector addition, then you can write OA vector plus B vector, OA vector plus B vector is equal to OP vector, and that OP is half of A vector. OA vector plus AP vector. AP vector is B by 2, so this is B by 2. So OA vector is half of A vector minus B vector. Similarly, in triangle OCP, if you see, then OP vector plus PC vector is OC vector. So OC vector is OP vector, which is A vector by 2 plus PC vector, which is B vector by 2. So this is equal to half of A vector plus B vector. So one of the diagonals is half of A vector minus B vector, and another diagonal is half of A vector plus B vector. So as I have already determined area of the parallelogram, so this area is OAPC area is it is equal to the modulus of the cross product of the adjacent side, that is OA vector cross OC vector. Now OA vector is half of A vector minus B vector cross half of A vector plus B vector, modulus of this one. So OC vector is this much and OA vector is this much. So now half is definitely a scalar that will come out of the modulus symbol, and so from here on we can say half into half is 1/4. A minus B cross A plus B. A vector minus B vector cross A vector plus B vector. So now if I expand it, A vector cross A vector is 0 vector. A vector cross B vector minus B vector cross A vector plus B vector, minus B vector cross B vector, which is again a 0 vector. So B vector cross B vector is 0 vector, A vector cross A vector is 0 vector, which I have not written. Now minus of B cross A can be written as plus A cross B. Because vector cross product is anti-commutative. A cross B is minus B cross A, or B cross A is minus of A cross B? B cross A is minus of A cross B, minus into minus it becomes plus. So since B cross A is minus of A cross B, so these two minus symbols, minus of minus will give you plus. So this is twice of A cross B. So 1 by 4 into twice of A cross B, you will get half of A cross B. So you get the area of the parallelogram as half of A cross B, provided A vector and B vector represent the diagonals. So if the diagonals are provided, the diagonals are indicated by A vector and B vector, then the area is half of the modulus of A vector cross B vector. If the adjacent sides are represented by A vector and B vector, then the area is just modulus of A vector cross B vector. So we can determine the area of the parallelogram either if its adjacent sides are indicated by vectors or if its diagonals are indicated by vectors. Next, suppose we want to determine some trigonometric rules using vector algebra. Let us start with problem. So suppose in a triangle it is required to prove A by sine A is equal to B by sine B is equal to C by sine of C. Now suppose there is a triangle ABC, side opposite to vertex A is small a, side opposite to vertex B is small b, side opposite to vertex capital C is small c. This is angle A, this is angle B, and this is angle C. So the rule is, it is called as the rule of sines, S-I-N-E-S. Small a by angle A is small b by angle B is equal to small c by angle C. Now, suppose we consider a triangle, so you have to prove this for any triangle ABC. So suppose we consider a triangle A, B, C, opposite to side A, suppose this is vector A, opposite to side C, this is suppose vector C, and opposite to B, suppose this is vector B. So I am representing the sides of the triangle by vectors. So in this triangle, if you apply triangle law of vector addition, by triangle law of vector addition you get vector addition. You can easily see that A vector plus B vector is C vector. So C vector is A vector plus B vector. So if you take the cross product of A with B, suppose let us find A vector cross B vector, what you will get is A cross. Instead of B vector, you can write C vector minus A vector. From this one, instead of B vector, we can write C vector minus A vector. So this gives you A cross C, because A cross A is 0. So A cross C you get. So if you take modulus, you will get modulus of A cross B is modulus of A cross C. Now, what is A cross B? From this triangle, A cross B is AB sin theta. AB sin theta. Sin 1. Now, while calculating A cross B, we know that it should be the angle between the direction of A vector and direction of B vector. But you see this figure, A vector is along this direction, B vector is along this direction. So, this obtuse angle should be taken here. This angle should be taken here as the angle between the directions of A vector and B vector. And if this angle is C, this angle is pi minus C, that is 180 minus C. Because A vector is along this direction, B vector is along this direction, so the angle between the directions is pi minus C. So this will be AB sin pi minus C. Modulus means no need of n hat because n hat is modulus of n hat is 1. A cross C. A cross C. If you see this one, A vector cross C vector, this is the acute angle B. Because A vector and C vector are in two different directions, the angle between them is this angle B. So this is AC sin B. Now sin 180 minus theta is sin theta, so sin pi minus C is sin C. AC sin B. So A will cancel out, you have B sin C is C sin B. Now you can write it as B by sin B is equal to C by sin C. We have proved a part of this one. B by sin B is C by sin C. So if you can proceed in a similar manner, you will get the other one also. That means if you calculate A cross C or you calculate B cross C, then you will get it. Okay, let me show that. We can always calculate B cross C and we will get another result from this we can conclude. So let me show this. So now we have proved a part of it. Let us find B cross C. If you remember, using triangle law, we already had A vector plus B vector equal to C vector. So here I can write B vector plus C vector. Instead of C vector, I can write A vector plus B vector. Instead of C vector, I can write A vector plus B vector. Now you see that B cross A will get, because B cross B is 0. So this is B cross A, which means modulus of B cross C is same as modulus of B cross A. Now what is modulus of B cross C? B vector cross C vector. If you take this direction, B and C, if you take this direction of B vector and this direction as that of C vector, then this is your angle A. Because this is angle A vertically opposite, so this is BC sin A. And B cross A, B vector cross A vector. If you are taking the magnitude, then you get the same angle. Because you are taking the magnitude, you are not concerned about n hat. B cross A, if you calculate n hat, is perpendicular into the plane, but we are taking the modulus, so it doesn't matter. So this is BC sin of pi minus C. So BC sin A is equal to sin of pi minus C sin C. So this is sin capital C. Angles are denoted by capital letters, remember that. So from here, B will cancel out. So, sorry, this is B cross A, so this is BA, sorry, BA. B cancels out. So from here I can write C by sine capital C is equal to A by sine A. So from this first and from this second one, B by sine B is C by sine C, and C by sine C is A by sine A. So ultimately we have A by sine A is B by sine B is equal to C by sine C. So from 1 and 2 you can say, from 1 and 2 definitely you can say that A by sine A is equal to B by sine B is equal to C by sine C. So we'll come across several problems. So suppose a triangle ABC is provided and you have to prove cos A is equal to B square plus C square minus A square by twice of BC. Now if you see this triangle, opposite to vertex A, the side is A. Similarly, opposite to vertex B, it is small b, opposite to vertex C, it is small c. So the problem could have been different. Instead of giving this question, the question might have been prove that cos B is equal to A square plus C square minus B square by twice AC. So it is symmetric, you can say. This problem is symmetric with respect to the vertex and the side. Or cos C is equal to B square plus A square minus C square by 2AB. And obviously with respect to vertex A, you can say cos A is equal to B square plus C square minus A square by 2BC. So let me denote the sides of the triangle with respect to vectors. Suppose this small a, this is vector A. Suppose this is vector A. This direction is that of vector B and this direction is that of vector C, suppose. So by triangle law, you can easily say that C vector is A vector plus B vector. So let me take the dot product of B with B itself. So now B square can be written as B vector dot B vector. If you remember the properties of dot product, then obviously you can say that B square is equal to B vector dot B vector, which means B square equal to, instead of B vector, I can write it as C vector minus A vector. C vector minus A vector dot C vector minus A vector. So this will give you C vector dot C vector, which is C square, C vector dot minus A vector, that is minus C vector dot A vector minus A vector dot C vector minus A vector dot A vector, minus is plus, and A dot A is A square. So this means B square is equal to C square plus A square minus twice of A vector dot C vector, because dot product is commutative. So C dot A and A dot C are same. So this I am writing as A vector dot C vector. Now what is A vector dot C vector? It is modulus of A into modulus of C into the cosine of the angle between them. So what I get is B vector equal to C vector plus, C square plus A square minus twice AC cos B. So this gives you cos b as b square. Sorry, this gives you cos b as c square plus a square minus b square by 2ac. Now this is just opposite to what is given in the question. If I could have taken c vector dot c vector, then I could have proven this. If I could have taken a vector dot a vector, I could have proven this. So it is symmetric, I already told that. So this is proved. In a similar manner, if you can note down, so cos b I have also proved. So now let me find a vector dot a vector, I will get this result. So instead of this one, let me write, this can be also proved because this is symmetric. Similarly, if you take c dot a, you will get cos c is equal to a square plus b square minus c square by twice ab. So now let me find a dot a for the sake of this question. So a square is equal to a vector dot a vector. Now a vector can be written as c vector minus b vector. So this is c vector minus b vector dot c vector minus b vector. So this will give you c dot c, c square minus b dot c dot b, sorry, c dot b minus b dot c plus b square, because b dot b is b square. So a square will be equal to c square plus b square minus twice of b dot c. And b dot c, if you take b vector dot c vector, the angle is again this direction is b vector, this direction is c vector. So this angle has to be taken into account, and this angle is equal to angle A. So you can say that a square is equal to c square plus b square minus 2bc cos a, because b dot c is bc cos a. So here on you can say that cos a is equal to c square plus b square minus a square twice bc. So this has been proved. So as I have already told, if you take c dot c, you can prove cos c is equal to a square plus b square minus c square by twice a. So there are a variety of problems in geometry and trigonometry that you can prove using vector algebra. Let me prove another geometric application. Suppose it is required to prove that the diagonals of a rhombus are perpendicular to each other. So you can prove that also. So the question is, show that diagonals of a rhombus are perpendicular to each other. Rhombus are perpendicular to each other. So let us consider a rhombus. Suppose ABCD is a rhombus. Whose diagonals are AC and BD. So suppose this is a rhombus ABCD and its diagonals are AC and BD. Let AB be represented by A vector and BC be represented by B vector. Obviously, the opposite sides of a rhombus are parallel and equal, so this is also A vector and this is also B vector. Now, let us find AC vector. Using triangle law of vector algebra, this AC vector, which is the diagonal, is obviously A vector plus B vector, and BD vector. Now BD vector is another diagonal. Now in triangle ABD, if you use triangle of vector addition, you will get A plus BD is B. A vector plus BD vector is B vector. So obviously BD vector will be B vector minus A vector. BD vector is B vector minus A vector in this triangle ABD. So let me take the dot product, and if the dot product is 0, then you can say that the diagonals are perpendicular indeed. So AC vector dot BD vector. So A vector plus B vector dot B vector minus A vector. So this is A dot B. A dot A is A square, so this is minus A square. B dot B is B square minus of B dot A. So as you know that the sides of the rhombus are all equal, so A and B is obviously equal. Modulus of A and modulus of B are equal, so A square and B square will obviously cancel out. So now A dot B minus B dot A. Now as you know that A dot B is equal to B dot A, so this is obviously 0. So since the dot product is 0, since AC dot BD is 0, if the dot product of two vectors is 0, it means that the vectors are mutually perpendicular. So we can say AC vector is perpendicular to BD vector, which was the requirement of the question to show that the rhombus, diagonals of a rhombus are perpendicular to each other.